Start these two sessions of today for me. So there'll be one this morning and one this afternoon. So I'll just first do a few more words on the topic of last time about the divisor function in arithmetic progression, and then today I will mostly talk about the original Zhang approach to bounded gaps between primes and try to motivate some of the steps in his method and bring out some of the key points and key difficulties in this work. And then this will lead to exponential sums of finite fields somewhat similar to the Klusterman sums we saw yesterday. And in the last two lectures, tomorrow and Friday, I will explain some of the main ideas and results for exponential sums of finite field. So let me start then by this quick reminder. So this will be quite fast. So yesterday we had something like, so we wanted to study the divisor function in arithmetic progression. So we had some smooth weights, V1 and V2, which we think that V1 is like the characteristic function of an interval of length m and V2 of length n. And there was this application of this Poisson summation formula, which gives an expression which is really close, at least in spirit, to a sum now with new variables h1 and h2, where the lengths have been symmetrized compared to the lengths of the original ones, and to get something that's exactly correct. Let me copy exactly what I had. So then we have Klusterman sums, where so SABC is the Klusterman sum defined as the sum over x invertible modulo C of E of AX plus B times the inverse of x modulo C, everything over C. Okay, and there is this theorem of André-Weil that tells you that, roughly speaking, you almost always have square root cancellation in the Klusterman sum. So if basically A, B, C that was co-prime, then modulus SABC is less than the divisor function of C times C to the 1/2. So for any positive epsilon, it's of size C to the 1/2 plus epsilon at most. And the point is that if you want to apply this, there will be some degenerate cases that you have to handle. So the way this is done usually is to just see what happens when you don't have square root cancellation and hope that you get something that can be evaluated explicitly that you then combine in the main term. If that doesn't work, then you can always try to check that these, you can try and guess what the main term will arise from and check that if you take, let's say, q equals 1, then this will lead you to the same expression with a factor 1 over phi of q to make the cancellation work out nicely. And this is indeed something that happens in most applications. And this is because the main term, in the most simple-minded heuristics to guess asymptotic of the divisor function in arithmetic progression, the main term is the right one. It's not like the prime number theorem where the main term is wrong if you just use inclusion-exclusion. So for instance, so the simplest case is when C is a prime. Then it's very clear what happens. There are two cases that you have to think about. And let's say that we view A and B as defined modulo C, which is a prime. So SA is BP, 0BP, if B does not divide, P does not divide B, well, you can see what happens. Then the A is 0, so you have x bar runs over all invertible classes again by just replacing x by x bar. So this is a Ramanujan sum. So it's -1. And if both A and B are 0, then this is the only case where the sum is large, and it's, in that case, p minus 1, which would be phi of c in the general case. So from this, if you suddenly take the case q equals a prime in this divisor function in arithmetic progression question, it's quite easy to see that the main term will only arise from a and b. So that means h1 and h2a both divisible by q. Because of the range of the variables, that means essentially that only h1 equals h2 equals 0 will contribute. Okay, because you have the sums are going to be too short to have contributions from other multiples of q, and you're going to get p minus 1 coming out from there, and from this you can detect the main term. So that can be kind of an exercise. Well, I'll leave this third board for later. So exercise then. So check main term arises from at least when q is a prime. So when q starts not being a prime, you usually have to do a little bit of additive or multiplicative sum elementary combinatorics to get exactly the right thing. Because you could have common factors of various sizes. So this usually involves some identities between multiplicative functions. But they are usually not too hard. And again, if this turns out not to work, in many cases, by just reversing the process with q equals 1 and checking to see what is the main term that comes out there that you can maybe compute independently anyway, you can check that it cancels out. Okay. So I'll come back to Kloosterman sums later. So just a few words now. So examples of a very general class of exponential sums for which we can prove this type of square root cancellation because they are related to algebraic geometry over finite fields. Okay, and so tomorrow and Friday I will explain some of the steps that are available, some of the techniques that are available to handle these things. So one typically emphasizes finite fields, despite the fact that C is really an arbitrary modulus. It's because using the Chinese remainder theorem and other types of techniques, it's most often the case that the critical situation is when the modulus is a prime. Okay, so in the case of Kloosterman sum, this is, for instance, what Kloosterman did in the 1920s. He introduced these sums for the purpose of studying the number of representation of integers by diagonal quadratic forms in 4 variables, positive definite, and he proved the first non-trivial bounds, which were not as sharp as that, but were sufficient for his purpose. Okay, I'll give some reminders of this history too. Okay, so let's go then to the third section. So it's really now about primes in arithmetic progressions. So it's quite possible that some of the things I'm going to say today will be relatively technical. Actually, they will be relatively technical. It's just the fact that what the type of techniques that's involved in Zhang's proof are quite delicate and complicated. So in comparison to almost everything else that you've seen in this lecture since the beginning of the school, there are steps which are very hard to motivate in a reasonable amount of time. So there are some steps I will tell you, okay, we do it this way, and I don't really know myself how you would motivate this deeply. I think there's a certain amount of trial and error that went into this work, starting from Fouvry and Ivanets in the 80s. Okay, so let me remind you of the motivation. So the goal now is to say something non-trivial and unconditional about so the exponent of distribution for primes. So let's say for the form angle function, which is almost the same thing, for moduli which go beyond the Bombieri-Vinogradov theorem. So because we want something unconditional, there's no hope of trying to get a strong exponent of distribution, because that would tell you something about the Riemann hypothesis that we don't know today. So we try to necessarily do the same type of averages as in Bombieri-Vinogradov. And in fact, one has to restrict these averages in various ways, because there's no known really complete analog of Bombieri-Vinogradov beyond square root of x. So let me give two motivations quickly for this. Actually, okay, I guess I can give three. So one is curiosity. And there's a natural boundary, which is square root of x, that arises from Bombieri-Vinogradov, which is actually a natural boundary for exponents of distribution for a very, very large class of arithmetic functions. So it's natural to try and see if we could go beyond that. Second motivation, one of the first applications of this was to the Titchmarsh divisor problem. So I remind you that this was the problem of studying the sum of the divisor function at p minus 1 when p is less than x. Okay, p minus 1 could be p plus any fixed constant, of course. So I told you, and I think you saw in an exercise, and nowadays it's really easy, that if you know the Bombieri-Vinogradov theorem and the Brun-Titchmarsh inequality, you're going to see that this is some constant times x plus big O of, well, let's say x over log x maybe. And this you compare with, to interpret this, one compares that with just the asymptotic formula for divisor function without restriction on n being a prime or p minus 1. And here there's something which is quite a bit different. There's a two-step asymptotic formula. Okay, so the application of Dirichlet's hyperbola method gives an asymptotic formula with two steps, or applying Perron's formula to zeta of s squared gives you naturally two steps, because zeta of s squared has a double pole, which is where you have first a log x and then an x. And now if you compare, you might say, well, if really the other term is just big O of log x and cannot be made more precise, this would show a difference between these two behaviors. So here we have a nice asymptotic formula with two terms and then quite a bit smaller term. Here we would have just one. Now if you just apply Bombieri-Vinogradov and Brun-Titchmarsh, you will not be able to get better than that. Or at least nobody has been able to get better than that. But if you use using exponents of distribution beyond 1/2, okay, so one can get a two-term asymptotic formula. For the Titchmarsh divisor problem sum. I called S of x before. Okay, so this was done, I think, independently by Fouvry and maybe Bombieri, Friedlander, Iwaniec. I would have to check these two actually. So that's one motivation. Now, second motivation is the one that's the motivation for Zhang, but this is the type of motivation that existed already in the 80s when Fouvry and Iwaniec started working on such things. And in the original GPY method, so this was a crucial issue. So original Goldstone-Pinz-Yildirim method. Okay, so I will spend a few minutes to recall this method. So it's a simpler version of what James described. I'll go back to this simpler version since with the new method, with multivariable type of cell block sieve, it's not a problem to, I mean, there's no particular point in emphasizing the original, but here to motivate this work of Zhang, it's actually useful to go back to what Goldson, Pintz, and Yildirim were doing. So what they did was the following. So they constructed kind of Selberg-like sieve weights lambda d defined for d less than some capital R, such that we have some kind of nice lower bound for the expression that tries to count how many shifted tuples for an admissible tuple contain at least one prime, which had the following shape. So this is probably going to be a bit too wet. So I'll erase both and use the third one for the moment. Okay, and so the lower bound looks like that. So you sum over integers in some interval of length x. Then there's the sieve weights, which are built using the lambda d's, which are, so it's bounded by d up to r. Then d divides the product of the n plus hi's. So here we have fixed some parameter k and an admissible k tuple h1 up to hk. Then there's the square that makes this non-negative to avoid problems. And then you want to count how many of the n plus hi's are primes. So this should really be some kind of characteristic functions of the primes, but for my purpose, it doesn't make any difference. And you want to say that at least one is prime, and this would be the case if this sum is non-negative, because this is at most log of 2x plus a constant. So if this is strictly positive, there has to be at least two primes. I said one prime, but of course you need at least two to get bounded gaps. Okay? And so what did they get? So this is exactly the type of expression that James was dealing with, except that he had a more refined version of the sieve weights here, and that allowed him to actually try to do it even with a multiple of log x instead of just to have a 1 here. Okay, and what is the outcome of the original GPY method? It would be an inequality like this. So there's going to be some theta, which of course will be an exponent of distribution, some kind. Then there's actually a second parameter, L, which comes in the choice of the weights. And in the original version, you get precisely that. So theta times k times 2L plus 1. So L is a parameter that's completely at your disposal, divided by L plus 1, k plus 2L plus 1. This would be the thing that comes out of the analysis of the von Mongol functions. And from the second term, you would get minus 1. This would be times x log x, roughly speaking. Sorry. Plus an error term. Okay, I'll put this error term in another location because that's what I want to analyze further. So the error term, roughly speaking, again, this will be very similar to things that James described. So you have moduli up to x to the theta. They are certainly square free, the way the thing is constructed. Then you have maybe some divisor function, to whatever, capital M, let's say, of Q. Then some power of log maybe M2, let's say. And the main thing is the error term in the prime number theorem. So delta, the discrepancy for lambda for x QA, and you have the maximum. So everything is there. Okay, so now if we want to analyze what happens, okay, so this is an exponent of distribution in the Bombieri-Vinogradov sense. So theta is an exponent of distribution for the von Mangoldt function. Okay. So we know we can take theta essentially 1/2. So let's look at the size of the first term. So of course we want this to be as large as possible so that we can subtract 1. If we think of the numerator and denominator, you see that if L goes to infinity and K also, but L is kind of smaller order of magnitude, maybe square root of K, then you have something like 2 times KL, and this is divided by K times L. So you have a 2 here, you have 2 theta minus 1. And so this is only positive if theta is larger than 1/2. So even theta equals 1/2 doesn't work. So then we need theta larger than 1/2 to get strictly positive main term, which is the goal, to get bounded gaps. Note in passing, I won't really comment on that, that even if you add the best possible theta, which is theta equals 1, I mean, you cannot control integers in arithmetic progressions where the modulus is larger than the length, you could not replace the 1 by 2. Okay? So that's in passing, that's one of the key advantages of the method of James, that he could take anything here. Okay, but of course, theta equals 1/2 is what Bombieri-Vinogradov gives, or even what the generalized Riemann hypothesis gives. So that was kind of very satisfactory at the time because I mean, we know 1/2 is a barrier and we see it appearing naturally. So I think it was very tempting to think that one could not improve the main term because of that. And of course, that was a big mistake. Okay. So what James did, and as you've heard also independently, tau, what they did was they improved the main term by better choices of the weights. And this is what I'm going to not talk about, since we already saw James's exposition of that. So by making this choice of weights more delicate, but much more powerful, they could improve the main term and say that, in fact, not even theta equals 1/2 is needed, but just anything strictly positive would suffice not only to get bounded gaps, but even with theta equals 1/10 billions, you could still get here with 1 replaced by an arbitrary m. Okay? But before that, there was the work of Zhang. And so he worked on the error term and tried to get a better bound for this error term, essentially. So improved error term. Right. And that's where one has to be very careful about one's language. Remainder term. Okay. So there's a number of things that go into this. So I'll first describe. I already stated the theorem last week, but I'll remind you again of what is the variant that he actually proved. There's some work to be done to check that this variant is sufficient, but it's not so impossible. So I guess I'll at least erase one of these to have it ready when I'm done on the other side. Okay, so I think this I can now hide because there's no problem. I mean, I don't need it right now. So more precisely, so there's a number of things that needs to be done. So first of all, and here I guess the way I define things, I should first put the maximum. So that's the most naive way to write things. So first of all, if you remember the proof of James, that's just a generalization of this, so you can look at your notes and see how this type of error term arose. You don't need an absolute value. I mean, of course, if you can bound with the absolute value, you're in good shape, but you don't actually need it the way this thing comes up. But then maybe you need something a bit more precise than just estimate, but that's not a problem. You would just have some maybe unknown arithmetic functions, but of sizes that you control. You don't need the maximum over all residue classes. So we don't need quite absolute value of delta lambda. You don't need all A mod Q, co-prime with Q, but only those which are roots of this polynomial, this function of n which arises here, modulo Q. A such that A plus H1, A plus HK is 0 mod Q. And so typically this will be, because Q is square free, this will be just K to the power, the number of divisors of Q. Okay? So if Q is a prime and large enough, then the HIs are distinct mod Q, so you get exactly K roots, and for every prime you get K different roots, and Chinese remainder theorem tells you that many. So that's K to the omega of Q, which is certainly less than Q to the epsilon for any positive epsilon of such A. So that's quite nice in the sense that, as I'll explain later, this number is not out of reach of the type of techniques that were available to Zhang, but we don't know where these A's are. They could be located anywhere, and so we cannot say that A is small. So if all the A's had been as small as the number of them, that would be much better. Okay. And the third thing is much less obvious. So the fact that you can take A to be that just follows from the method immediately. Much less obvious is that you can assume that Q runs over smooth numbers, so more precisely, arbitrarily variable numbers. It's always square free. Moduli. So this is not obvious. This is the type of things that experts in sieve theory were kind of aware of, and that suddenly was explicitly noticed by Motohashi and Pintz a few years after GPY came out, although they couldn't exploit that observation. So if you remember, you can kind of have a very vague guess that something like this might be true. If you remember the way the thing came, the Q is not really a fixed Q. It's always going to be the least common multiple of 2 of these R's in the cell box sieve. So this Q will always have at least one factorization. And now if you could arrange the factorization to have many prime factors and so on, you could hope to get something like that. So if you just take this naive observation of cell box sieve, you just know you have one factorization, and you could try and exploit the two variables R1 and R2. Typically, this is not flexible enough, but at least it exists. Okay? All right. So the outcome is that it's enough to go beyond the Bombieri-Vinogradov theorem when you have this type of restrictions removed. So the following result suffices to get bounded gaps. So that's the same theorem I stated on Friday, but I will restate it again. So this is the theorem of Zhang. This is the kind of slightly stronger version in the Polymath 8 project. And it goes as follows. So we have, so for any saving power of log that you want, for any positive epsilon, for any non-zero integer, so you sum over Q, square free, less than or equal to x to the 1/2 plus 7 over 300 minus epsilon. Okay, I got my quantifiers wrong again. I need there exists positive delta such that, so Q is coprime with A, and Q is X delta smooth, so friable. And in fact, you can put the absolute value. So this first observation somehow is more like a psychological thing. It's more the fact that you can take friable integers that's crucial in this argument. So I'll just write it this way, psi of x QA minus psi of x over phi of q is less than x over log x to the a. Okay, and here it's very important, this depends on epsilon, or it may depend on epsilon, on a, and on whichever choice of delta. There might be more than one choice of delta for a given epsilon, but it does not depend on small a. This is uniform in terms of a. That's the crucial thing for the application to the GPY method. So this is significantly weaker if you allow the implied constant to depend on small a. It's significantly weaker than results of Fouvry-Vignettes and Bombieri-Friedlander-Vignettes. But of course, for the GPY method, that's the key thing, that you need to be able to have a uniformity in A. Okay, the 7 over 300 has no meaning. Any strictly positive number instead of 7 over 300 suffices. Zhang's work was something like 1 over 1,200 or something like that. And he certainly did not try to optimize anything. So the fact that this is significantly better represents a certain amount of work, but it is not a crucial feature of the work. Okay. Now I'm going to erase one of these without getting it too wet. Okay, so this we have already discussed. Okay, so what are some of the steps? So I'm not going to be able to give you even anything that remotely looks like a convincing sketch. I just want to try and point out some of the key ideas and some of the key features, like in particular, why can we hope to have things which work for any A? Why is it unrealistic at the moment with these methods to try to put a maximum over A? This is not known. What is it that one gains by restricting to sufficiently smooth moduli? So this is things I'm going to try and explain, but certainly from what I'm going to say, you should not get the impression that this is easy or that I've explained most of the work. So some key steps. Right. Okay, and many of these key ideas are exactly the same as were found by Fouvry-Vignettes and Bombieri-Friedlander-Vignettes. Somehow just there are some key observations of Zhang that allowed him to detect that this was the key type of statement and to prove it using some of the same steps as Fourier-Vignet's and Bouvet-Friedlander vignettes, but going beyond what they had been able to do. Okay, so the two steps that I'm going to describe. So the first one is kind of classical. It's the same step as described by Sound in the proof of the Bombieri-Vinogradov theorem. We try to exploit multilinear or bilinear decompositions of the Form-Mangold function. Multilinear decompositions. Okay, so it's not easy to make things work with the type of bilinear description that Sound explained. I mean, one of the things that the Polymath project realized that, in fact, it could have been done a posteriori, but a priori you need more flexibility. I mean, in Zhang's work, he needed more flexibility, so he used some different decomposition, which has more flexibility built in. That's the so-called East-Brown identity, which I will describe. It's complicated looking, but it has this key flexibility property, which is often very helpful, at least in trying to find the first proof of something. Okay, and then the second step that I will describe is the bilinear estimate, up to where we reach exponential sums over finite fields. Okay, so in the original work of Zhang, he could not succeed with bilinear estimates. And again, it was realized in this Polymath project that it was in principle doable with worse exponent than 7/300. So there was a third step, which was a trilinear estimate, about which I'll probably not say much, but maybe I'll have time to mention it. So this trilinear estimate is very much related to bounds for the exponent of distribution of the ternary divisor function for tau 3 beyond 1/2. Okay, so let's go into bilinear decompositions first. Okay, so first, one key reminder of why this is useful. So again, this is something that Sound discussed in the context of the large sieve, which was the instance of a highly non-trivial bilinear form estimate that's extremely useful in analytic number theory. So I'll just remind you of why this is useful. So call that to bound a sum. So bilinear sum means something like you have two variables m and m, coefficients alpha and beta, and then kind of coefficients like a kernel k of mn that exist. So we are looking at a sum like this. So maybe alpha and beta are quite specific. So these were the type of things like that arose in the decomposition of the Form-Mangold function that Sound described. There would be truncated Möbius function, logarithm functions, things like this. So they could be quite explicit, but we don't want to use specific features typically because in many cases we cannot exploit any feature beyond something like the average size. So we view this as arbitrary, except for, let's say, that the mean square size, the Euclidean norm, is controlled. And these are some coefficients which maybe are oscillatory coefficients. So we expect some cancellation in the sum. And Sound explained why this is not a vain hope, even if you don't know anything about alpha and beta, provided this is a genuine bilinear sum, which means that it has to be that none of the variable is too short. It cannot be just a linear form that you use. So let me call this B. Okay, so if you think of this as wanting to get an estimate for B with this type of restriction, well, the only thing you can say is that it's bounded by the norm of the corresponding bilinear form times the norm square of alpha and beta is the best possible, where delta, well, it's not a discrepancy here, is the norm of this bilinear form as a map between two Euclidean spaces of the linear map with coefficients kmn. I guess either way, well, I guess it doesn't matter. Okay, if m and n are the lengths of the variable. Okay. And so the large sieve, the way he proved it, well, the first proof was based on this duality principle, which was observing that the norm is also the norm of the dual operator and exploiting the fact that this dual operator, in the case of the large sieve inequality, is somehow easier to handle. Okay, but the typical way this is done is not to apply some abstract linear algebra or analysis formula. So the typical estimate is always repeated many times, is to choose one of the variables and apply the Cauchy-Schwarz inequality. Let's say we view this as a sum over m of alpha m times the remainder. So you would have that. Sum over m, sum over n, beta of n, kmn. Okay, so I put the square so that I don't have to put the square root. So this is the norm of alpha. And then you open the square. Now you have two sums over n1 and n2. Beta n1, beta n2, conjugate. And then the sums, of kmn1, kmn2 conjugate. Okay, and the key point is that in many cases, this study of the second sum will split into two components. There will be the so-called diagonal components where kmn1 and kmn2 are essentially the same thing. So then it's a sum of positive terms, cannot get any cancellation. But we hope there are not too many of them. So there's always certainly n1 equals n2 in the diagonal. That's kind of visible. But there could be other cases. So sometimes the diagonal is more than just given by n1, n2. But somehow the hope is always that this diagonal, if you think of the pairs of two variables as being a two-dimensional set, that the diagonal is defined by equations that are kind of one-dimensional. So that the number of diagonal terms is quite a bit smaller than the total number of pairs n1 and n2. And then there's a non-diagonal where you want to get a better bound. So you get a better bound. So what does it mean typically to get a better bound? Well, let's say that we assume that k is of size roughly 1 on average in absolute value. So this is a sum of size capital M. So diagonal terms would be of size capital M. And here we would want something that like m to some power 1 minus something. Like optimally would be square root cancellation, square root of m, but that's kind of an unusual feature in the very general case. So big O of m to the 1 minus something, c, small c. Okay, and there's often a game to be played because of these bilinear forms typically depend on much more than these two variables m and n, as you will see in this sketch during the afternoon lecture in the bilinear estimates of that come in the proof of Zhang's theorem. The number of variables is kind of large, and you can combine these in different ways. And there's a game to be played, for instance, to ensure that the diagonal contribution and the non-diagonal are actually of the same size, because that's when the thing is optimally balanced. And this is a type of flexibility that will typically come from, well, having smooth moduli. So the large sieve estimate is very unusual in the fact that one really gets basically optimal estimates for the diagonal and for the non-diagonal terms. In actual situations, in more complicated settings like this type of theorems, you will get estimates which are quite complicated and that are non-trivial for various ranges of m compared with n. So often, non-trivial results are only obtained with restrictions on the range of m and n. So this only is something you saw in the proof of the Bombieri-Vinogradov theorem, except that in that case, things are really very nice, and there's basically no other restriction than both of them has to be not too small. But in the type of things that comes in Zhang's estimate, we'll see that, for instance, there'll be one range n which has to be relatively close to square root of x. Okay, and that fact means that when you do your bilinear decomposition of the from-angle function, you cannot just take these parameters capital M and capital P in the variant that Zhang described to be basically anything. You sometimes have to work a bit harder, and it can happen that there's no good choices if you just do this standard like Von identity-like bilinear decomposition. So this might not okay, so if you look at the old papers of Fouvry-Ivagnetz and Bombieri-Friedlander-Ivagnetz, typically they use just bilinear decompositions. They estimate them in many different ways with 3 or 4 or 5 different treatments, which are non-trivial in different ranges, exploiting the flexibility of the Eastbourne identity that I will describe in a few minutes. And then there's the final step is some combinatorial things where you have to show that whatever ranges of the bilinear forms you can put into one of these non-trivial estimates. And in the Zhang original work, so we had bilinear estimates which did not quite cover the whole thing, but he could understand what was the non-covered part that had to do something that he could study using trilinear forms instead of bilinear forms in the setting of the Eastbourne identity, but not general trilinear forms. The coefficients were actually smooth variables, like smooth functions. And so we could use things about basically the divisor function, ternary divisor function in arithmetic progressions. Okay, so I'll try and explain that now. So I'm pushing back and back the actual technical stuff, so only the afternoon session will be really not so fun. Okay, on the other hand, I'm going to now state the Eastbourne identity, so it's going to be a bit painful. Okay. So what's the Eastbourne identity? And I now want to explain why it is, for some purposes at least, much better than the kind of more naive identities like sound motivated last time. Okay, so to get optimal flexibility, the best we know at the moment, and I think there's a blog post of Terry Tao where at some point he tried to kind of motivate and justify that potentially this should be the best flexibility one can get for bilinear decompositions. I think there was something like that. So we use, or one uses, Eastbourne's identity. So there would be an identity of Linic which might be used with almost the same flexibility, but it has a few defects which have the consequence that most people tend to use Eastbourne's identity. So it goes as follows. Okay, so you have an integer parameter capital J, some big integer capital X, and you're going to study the von Mongol function for n up to x, essentially. More precisely, you can do it for up to 2x. Okay, then it's a formula for the von Mongol function. So being a formula, you can only check it in a few minutes in your head. So minus the sum from 1 to capital J, minus 1 to the power j, binomial coefficients of capital J over J. So in applications, J is typically a fixed number, could be quite large. It's 10 in Zhang's work. This is then a bounded sum with coefficients, which are also bounded, so it's certainly not a problem. And then you have a huge sum with first capital J variables, actually small j variables, but in applications, it's typically the case where small j is capital J that kind of gives the worst bounds. So, but for each j, you have this number of variables. These are short. Okay, so they're at most x to the 1 over capital J. But they come with coefficients for which you cannot say much at this point. So there's the Möbius function. So these coefficients are certainly bounded. Their average mean square size is certainly understood. But because x is really small, I mean the variables are really small compared with x, you cannot say too much about their sums uniformly on the various parameters. Okay, and I'll continue here. And then there are some new variables n1 up to nj, constrained to have the property that the product of the m's and the n's is equal to n. So n has to come up somewhere. This is a formula for the von Mongol function at n. But now you have nice smooth functions. Okay, more precisely, one of the variables has the log as a coefficient, the other one variable has just the 1 as coefficient. Okay, so the interpretation when you sum over n the von Mongol function with any other weight will be to transform it into a sum of various 2j linear forms where j is this parameter that you have at your disposal. And there are 2j linear forms with m smooth variables. So this could be quite long when you sum for n less than or equal to capital X. The n's could be quite big. And you have j other variables that you don't really know much about, except that the variables, the coefficients are bounded and they are very short. Let me give here a hint of the proof. So it's quite similar to the type of things that Zhang was described and could probably be obtained by refining the type of motivation he was giving. So the proof is to compare coefficients of n to the minus s in the obvious identity that I certainly will not remember, so I have to find it somewhere. So you will see it's very similar to the identities that Zhang was writing. So zeta prime over zeta, 1 minus zeta times m to the power capital J is zeta prime over zeta plus the sum from 1 to capital J minus 1 to the small j, binomial coefficient, zeta prime, zeta to the j minus 1, m to the j, where m of s is the truncated Möbius Dirichlet series, where n is at most x to the 1 over j. So this identity is obvious by the binomial coefficient, binomial theorem. The coefficient of n to the minus s in this thing is exactly minus that by just expanding the Dirichlet convolutions. This is von Mongol, so you just need to say that this is supported on an integer larger than x, or 2x. That's what I claimed. We only need n up to x anyway. Okay. So how is this used? Okay, so this means we can interpret sum of lambda of n for any weight k of n as a combination of multilinear expressions something like sum over n1 up to nj, alpha n1, alpha n capital J, beta n1, m1, m2 capital J, times f k of the product okay, as I said. So these would be smooth weights. So by doing localization and separation of variables, you could assume that each ranges over mi of size close to capital Mi with very good localization, like for instance, like yesterday from capital Mi to capital Mi times 1 plus 1 over log x to some power. And these are controlled size on average and very short. Okay, so it's usually customary at least also to localize them for Ni of size capital Ni, and capital Ni is then quite small. And the next step is then, if you want to just use bilinear form techniques, well, now you glue variables. So you have 2j variables, and you divide these 2j variables in 2 blocks, and you put the convolution of the respective blocks in one big variable, the other blocks in the other one, and you will get something like a bilinear form. So, okay. So I'm sorry, I will have to hide the smooth part of the Eastbound identity. And I'll use this one. Actually, maybe I can use, yeah. Oops. This one doesn't work. Okay, so I need at least one blackboard. That's kind of not too. Okay, so I hide the proof of this Eastbound identity instead of the smooth part. But as I said, it's an identity. How hard can it be? Okay. So glue sum of the 2j variables in some new variables of size, let's say, capital M. The remainder in n of size capital N. And then you get something like sum of some new coefficients, alpha tilde of M, beta tilde of N, k of M times N, where M is of size capital M, N is of size capital N, and typically Mn is very close to X. Because very often you can bound trivially contributions which are slightly below capital X. And so in these bilinear forms, you will only need to, or these multilinear forms, you will only need to handle this type of ranges. Okay? And you see there's lots of flexibilities. But the flexibility is not complete. If all the variables were very short, it would be just like having smooth numbers where you can put like the two ranges where basically wherever you want. But here we only have a good control of the size of the alphas. So if you have a gluing like that and you still have one of the alphas here, you can replace m by something slightly larger and n by something slightly smaller by patching, getting one of the non-smooths to the other one. But if you're playing with the long ones, or potentially long ones, it's harder to manipulate and to have complete flexibility. So from this point of view, you can kind of understand why this might not cover all the ranges where you have good estimates. Okay, it's already 10 o'clock, so maybe it's a good time to stop. So this afternoon I will state what kind of bilinear range Zhang is able to prove. These are statements of independent interest. So these could be useful for something else than bounded gaps. The bilinear estimates can certainly be useful also for other purposes than bounded gaps. And I will explain, or at least give you indications for why, at least in the type of estimate that Zhang proved originally, this does not cover everything. There's a small range, but in this small range, he was able to rearrange not in 2 blocks, in fact in 4 blocks, but 1 block was very short, and the other 3 blocks were only coming from the smooth variables. Okay, and convolution of 2 smooth variables remains smooth. So the fact that it's not just one of the m's is not a problem. Okay, so I'll explain that this afternoon and then try and explain the proof of the bilinear estimates. Thank you. Any questions? Yes?
I'm a bit confused by what you mean by like glue some of that.
Oh, right. Okay, so I didn't want to write it down because if I write it down, but I can give it on an example. I mean, writing it down makes it even more confused for most people, I think. So suppose, let's say that you have, I guess, right. And here, of course, my problem is that sorry. The betas, of course, are not the same. I mean, the betas are kind of almost the same because it's either log or a constant function, but after partition of unity, they would not be quite the same. And here the alphas, again, they are the same here, but after partition of unity, they might not be. But suppose you have something like sum over n1, n2, m1, m2, m3 of alpha 1, alpha 2, alpha 3 with n1, n2, n3, n1, n2, beta m1, beta m2, beta m3. And suppose you want to glue, let's say, n1 with m2 and the remainder n2, m1, m3. So this would be the sum of alpha tilde. This would be m, this would be n. Alpha tilde m, beta tilde n, and whatever other coefficients. And let's say alpha tilde m would be the sum, because here you have some k of the product, would be the sum over n1, m2 equals m of n1 is alpha 1, m2 is beta 2, I guess. Sorry. So this would be of n1, beta 2 of m2, and beta tilde m, you can imagine what it is. Okay. So that's what it means to glue variables. Any other question? Okay. Then we'll have coffee.